these issues. Thank you very much for Java for inviting me here, and thank you to Paulo, who is basically helping me resolving this charger issue. Thanks to all of you for your precious time. So basically, I'm gonna. It's my great pleasure to be here to meet with you and talk with you. Today, I'm just gonna focus on our research about the auction, about what we call the auction assistant AI systems in the cloud edge continuum. So I'm going to structure this talk in the following outlines. So firstly, I'm going to elaborate the first topic, that is the cloud AI inference via model ensembles from auctions. So as you can see, I'm going to talk about the problem scenario, the modeling and formulation, the algorithm design, performance analysis, and also finally the experimental evaluations. And we're going to spend a considerable, major part of this talk here. And then I'm going to very briefly also mention our, two other pieces of our work, like edge AI inference via auctioned edge resources, and also the foundation model fine-tuning with auction-based pricing. Lastly, I'm going to talk about some future directions along this line of research. So that is basically the outline. So for the first part of this talk, we're going to focus on the cloud AI inference via model ensembles. So the problem scenario is basically as follows. So as you know, mostly in a lot of applications, in a lot of services, today we are using this cloud AI service. I mean, the service itself is hosted in the cloud. It's in the remote data center, right? Whenever you are logging into Gmail, you are using spam detection. Whenever you are browsing your Amazon shopping webpage, or if you are viewing YouTube videos, you are using implicitly this online recommendation system, which is essentially a kind of AI service, hosted by Amazon and YouTube respectively. So basically, those AIs they are running in the cloud, which is usually a remote data center. But unfortunately, these AI models, they are deploying some kind of AI models in the backend, right? That's how they provide those kind of recommendation services to us. But the accuracy of these models can decay over time because of the concept and data shifts. So what that means, this basically means, the previous model that you are using, is not a good model at all, right? Why is not a good model at all as time goes? Because the user behavior is changing. For example, if you are browsing like YouTube videos, if you focus on tech videos, technology videos, and then YouTube will know, this guy has a lot of tech video browsing history. So in the future, it would be most likely this guy is again browsing these tech videos, right? That is a kind of behavior. But if you suddenly switching tech videos to like politics videos, right? Then that model does not work because your history is still tech model, tech videos, but your intention is the politics videos. So the previous model, which predicts your tech video browsing behavior based on your history of tech videos, does not work, right? Because you have proactively or passively change your behavior. I mean, as a user, we can change our behavior at any time, right? We are free, we can do that anytime. That is basically something called a concept. So that concept here basically means the underlying machine learning model behind. So that model needs to be adapted, right, in order to adapt to your new behavior. So if you do not adapt to those models, then the accuracy of the existing model is usually not satisfying. So in this case, you may want to retrain a model, right? But you may not have sufficient data because your behavior changing is all of a sudden, right? You do not have any history data. Your history is like tech videos, right? But now you want to browse on the politics videos, and also you need to spend more time more time to collect the sufficient data. And also sometimes this retraining is basically not feasible, right? Because it will incur a lot of system performance. If you are a small edge AI or small AI business, this kind of overhead may not be affordable. So there is basically one solution which is already told to us by the machine learning community. So they say that we do not have to retrain model. We just complementary retrain models. Like you use now instead of using one single model, you are using a set of pre-trained different models. So you combine these models. Some model is more accurate for this behavior, another model is more accurate for this behavior. So eventually, if you combine all of them, so we expect that this combination, or in other words, this ensemble models is supposed to be resilient to the model and to the concept of data drift. So why we need a
Do you think this is the recording for future use of the recording?
Yeah.
More towards the microphone.
Yeah, sure. Yeah, I can just stand here. Yeah, no problem. Yeah, no problem at all. So why we need something like auction? Why we need an incentive mechanism here? Because so here what we want is that we want to construct an ensemble, right? By the models. You can train those models on your own, but it might be not feasible. So an alternative way is that we can just acquire those models from external entities, whatever external third-party entities, right? So we can call those entities as model providers. So they are training models, right? But I mean, why are they training models? They do not want to spend their resources training models. So they would like to train models as long as there is a monetization mechanism. I mean, we pay them, right? So we pay them. So how can this payment happen, right? So there are a lot of, you can directly, you can ask them to price their models. So you buy their models by at whatever price they are asking for, right? An alternative way is that let's conduct an auction. An auction means that this cloud AI service, which once this ensemble is acting as an auctioneer, on the other hand, those model providers who are responsible for training models, they are acting as bidders, right? So they provide their models, and for each model that they provide, they have a label which is a dynamic price. So the auctioneer, can decide whether you want to buy the bid, basically whether you want to select those bids, which bids are the winning bids, meaning you're going to buy this bids, and which bids are the losing bids, meaning you're not going to buy those bids. So this is basically an auction here. We can construct the auction in this case, and also the auction has many advantages, as we know. So then we want to leverage the auction here, but what is let's going back. I mean, what problem are we essentially solving here? So we're not conducting auction is on one hand, right? But auction is just a part of the picture. It's not the entire problem. So the entire problem here is that we are trying to we are now standing from the cloud AI service perspective. So we are trying to optimally operating the system, optimally operating the cloud AI system by on one hand assembling this ensemble and performing the joint inference by these models in the front end. But simultaneously, we are also doing auctions and managing those models in the back end. So this is like a joint problem. It is not a separate problem. If you just handle each component separately, the performance of your entire system may not be globally optimal, right? So we consider them as a joint problem. So unfortunately, we are facing many challenges for this problem. So these auctions, we're not gonna having one auction. We're gonna have many auctions, a different auction, a sequence of auctions. So there are interdependence of those auctions. So each auction is not a separate auction. If you treat each auction as a completely separate auction, in the first auction you have you choose to buy models ABC. Second auction you choose to buy models CDE, right? Third auction, you buy a different set of models. Then if that is the case, then you are going to switch, from model ABC to model BCD. There are a lot of switching costs, right? The switching cost by downloading those new models, set up those environments, the performance like that. So that is basically what we mean by interdependence across sequential auctions. So we can just imagine that on the other hand, if we just keep buying model ABC, right? For the first auction, continue to buy model ABC in the second auction, that might be not the best solution, but there is no switching cost, right? We are avoiding the switching cost. So there is a natural balance between, the model performance, what are the best models that we want to buy, and also the switching cost, right? We want to switching cost. So second challenge my system inference performance. So if you have a large model, you have which consumes a lot of system resources, but on the other hand, the better performance. So there is always a trade-off in those types. And the last challenge, as we recognize, is that we need to balance the economic guarantees with sustained participation. So what are that? It means, if you are a bidder, you are creating a model. If this model is not chosen by the cloud AI service in the first auction, if it's not chosen in the second auction, third auction, so we have a model selected, get paid. So they are willing to continuously participate. That is why we always do the economic guarantees each single. So, what have we done exactly in this work? So basically, we are trying to we're using a mathematical language to capture and formulate this problem. So it is an optimization problem, right? And then we design our algorithms to solve this problem to control the system operations, right? So the system needs to assemble the ensemble, performing the inference, conducting auctions, managing models. It has several operations, right? It has several control operations. So we need to design the algorithms to get these control decisions, so that the system can implement those control decisions in order to control the system operations. And then we prove from a mathematical matter, we prove the rigorous performance guarantees of our algorithms. And then finally, we conduct evaluations to validate the system performance under our control algorithms. That is basically what we are doing in this work. So we start with modeling and formulate this problem. So basically, we have a cloud AI service, right, that continuously conducts a series of auctions upon and also performing the inference upon stream of data samples. So this system is slotted. So we have time slot 1, time slot 2, each time slot can be 1 minute, or each time slot can be 1 hour, depending on the service provider's preference and the system needs. And then data samples that arrive at time slot t, this small t is an arbitrary time slot here. So we have a set of data samples. The set of data samples is represented by mt. So every single data sample can be indexed by first data sample, second data sample, and until the last data sample. So for every single data sample, we have its feature, and also we have a label, right? We have branches label, and also we this cloud, we are considering one cloud AI service. We're not considering many cloud AI service. So this cloud AI service we assume that it has at least one model, right? Otherwise, how can the service be provisioned? It must have at least one model. It try to purchase those external models from other model providers. So for that one single model of this service owned, so service the cost of using, deploying, hosting this its own model is represented by ET. This ET can be energy usage, can be in terms of resource consumption cost that is hosting that is related to hosting this model. And then we have a minimum number of models for the ensemble, right? Because we are trying to construct a combination of set of models. So what is the minimum number of the models that you want to have? So this part is from the cloud AI service, and then we have the model providers, right? So the cloud AI service here is basically acting as the auctioneer, and the model providers here is basically acting as the bidders. So we have unmodel providers, and we assume without loss of generality, we assume that every single model provider only provides one model, right? If one provider provides multiple models, they can just be simply treated as multiple virtual model providers. So without loss of generality, just assume that one model provider provides one model. So every model has a cost. The cost of downloading the model from the provider. I mean, the model provider can be anywhere, right? Model provider can be another cloud provider. It can be a whatever system service provider at a different country, at different location. So this cloud AI service here needs to actually download the model from the model providers. And also, similarly, it has a hosting cost, right? So here we have the hosting cost of hosting the service provider's own model. So here we have a hosting cost for hosting the model N from the model provider, right? So basically every model has hosting cost. And then we consider this variation. I mean, this model, because this model is provided by the model provider, right? So the model provider can retrain the model due to whatever reason, can update the model. So we track whether the model has been retrained. Basically, the model has been changed from the last time slot, or the previous time slot is T minus one, current time slot is T, right? Whether the model stays the same or has been changed. And then we talk about the auctions, right? This auction is part of the system. So as we can see, the auction can be considered consisting of multiple steps. The first step is basically each bidder N here, the bidder N is the model provider, and some right? The bid contains the bidding price, of course, is the selling price, which is the selling price here, and then it contains the model itself, or the decision function of the model, right? Every machine learning model has a decision function associated to the model. And then it has this delta here. The delta basically here means it's a track, right? It tracks whether the model has been changed compared to the last time slot or not. So this is the bid. This entire thing is a bid. This bid is submitted to the auctioneer or to the cloud AI service. So the auctioneer, which is also the cloud AI service, will decide which bids are the winning bids, right? So basically, you're selecting the bids. You select part of the bids and the winning bids. And on the other hand, for those winning bids, you need to make a payment to those winning bids. So the payment is not necessarily the asking price here. The payment can be the asking price, but it's not necessarily the asking price here. So, and then you communicate the auction outcome to all the participants of the auction. The third step is that you just download the model from the winning bidders. If this model is not previously downloaded, or if the model has been changed since the last time it was downloaded. And so the last step is to send the payment to each bidder. So this is a very natural process. So what we are trying to do here is that here we are trying to model, what we should include in the bid, right? And also we need to pay attention that this payment is not necessarily to the asking price. So why is that? Because later in this presentation we're going to talk about the economic guarantees or the economic properties of every single auction. So which is really the individual rationality and truthfulness. So there we're going to see that in order to guarantee those properties, this payment is not necessarily the same as the asking price. So this happens on the back end, right? So what is happening in the front end is performing the inference. So remember that now we have an ensemble of models, we have a set of models. So we are using this set of models to conduct a joint inference on every single data sample, right? So then what's going to happen for each data sample? So here we have another 4 steps, and these 4 steps basically happen for every single data sample. So the first step is that this data sample just arrives from an end user with feature, right? And when this cloud AI service uses the purchased model, this model is from one of the bidders or from one of the model providers and its own model to calculate the inference result, right? This is remember that this HNT here represents the decision function of model N here. So this HD without the subscript N here represents the decision function of the cloud AI service own model. And then these inference results are combined. So here, there are many ways to do this, but here we just consider a very simple way of combination. That is, we calculate the combination as a weighted sum of the inference results. And then the next step is the ground truth label comes, right? It arrives from the same user. So here, this BMT hat represents the inferred model, and this BMT represents the ground truth label. Inferred label. This is the ground truth label. So by this ground truth label and the inference label, what we're going to do is that we can calculate a loss, right? Using what a squared loss function, whatever loss function, we are going to be able to calculate the loss. And then that loss value can be used to update the weights here. This alpha and beta here is a weight. And now we need to note that the subscript here becomes m plus 1. This is m plus 1 because it's for the next data sample, right? It's for the next data sample. And then basically this loop starts again, right, for the next data sample m plus 1. So this is how we conduct this ensemble learning, right? We are using ensemble of models to do a joint inference instead of doing a separate inference. So this is basically what happens in the front end of the service. So now we know what happened in the back end of the service and what is happening in the front end of the service. So then what are we, how can we actually control the operation of the system? Specifically, what are the control decisions? What are the control decisions? So we have multiple control decisions. So for example, the first control decision is a bid selection, right? Which bids the bid n here, whether bid n is selected as a winning bid or is not selected as a winning bid. And then, whether the model is deployed or not, right? Whether the cloud AI service needs to deploy its own model or it needs to deploy the models purchased from the model providers. And then we have the weights, right? We have the weight alpha, we have the weight beta. That is basically for the models, right? The alpha is for the models of the purchased model. The beta is for the model of the cloud AI service own. And then we have this payment. This payment is that if for the losing bid, the payment is always 0, right? Because you do not buy that bid. But for winning bid, you determine what this payment should be. So we have a set of decisions to determine, right? And then having our modeling of this problem, having our control decisions. So next, what we are going to do is that we need to pin down what exactly is the optimization problem that we are trying to solve here. So we consider the cost of the auctioneer. The auctioneer is also the cloud AI service. So the cost of hosting the models, the cost of downloading the models, and the payment is also kind of costly. And also the inference loss, right? Inference loss. So as you can see here, we are considering a squared loss function here. So this is the cost of auction. Then we have the cost of the bidders, right? The cost of the bidders. So the cost of producing this bid, right? Because the bidders or the model providers, they are doing their training, right? This is the time, effort, energy, whatever resources are training, producing this bid, producing the model. So this is the cost. This is the cost for this model provider to produce that model or to produce this bid. And also it needs to subtract the payment, right? Because the payment is a kind of revenue, right? It's not a cost, but if we want to consider that as a cost, so we consider that as a negative cost, right? So then we have this social cost, which is basically the total cost of all the parties within this auction. So we have the cost of auctioneer, cost of the bidder. So if you sum them up, we have this social cost. So in the social cost, the payment cancel, right? Because the payment here is considered as a negative term. Payment here is considered as a positive term. So the payment term will be automatically canceled. So this is a very normal situation, is a very normal case for social cost modeling. So what we're going to do is that even though the payment has been canceled, but the payment still needs to be determined, right? Because we need to determine what is the exact payment that we need to pay to the winning bid. And also the payment is going to relate it to the economic guarantees or the economic properties as we're going to talk about later. So now we have that objective function, which is basically the social cost on the previous slide, all the costs here, right? All the costs here. And then we have a set of constraints. So as you can see, the first constraint is that we need to show that our ensemble, we need to meet or satisfy the need of the minimum requirement of our ensemble, right? This capital W represents a minimum number of models that we want to host in our ensemble. And then this auction has a budget. Every time, every auction you have a budget. This budget, I mean this W and this QT, this capital QT, which is the auction budget, they're all provided by the cloud service. Right? The cloud service should determine how many models you want to use for your ensemble and what is the upper limit of your budget. This information are all provided by our service providers. And then we normalize the weight, without loss of generality. We think that the sum of those weights can be 1. And then we have some dependency constraints. So basically, if a model is not purchased, the model should not be deployed, right? But if you purchase a model, you can deploy it, or you do not have to deploy that, because we also want to minimize the switching cost, right? If you keep the models the same across auctions, you have no switching cost, but otherwise you're going to incur the switching cost. So finally, maybe let's take a look at this kind of beta participation. So as you can see, if we sum up all the participation of each bidder, so we require that there is a minimum number of times that bid needs to be selected as a winning bid. So basically, here we use this t to multiply this phi n, right? Because in this case, this phi n can be normalized as a fraction between 0 and 1. So if this phi n is a fraction, and then you just put t here, so t times phi n is going to be the minimum number of times for the bid n to win the series of auctions, right? So this is our control decisions, as we have just talked about in our previous slide. So this problem P0 is basically the problem that we want to solve. So our goal here is to design an online algorithm that can make those control decisions on the fly. That basically means as time goes, you have the first auction, so you make the decisions for the first auction, and then you have second auction, so you make the decisions for the second auction. I mean, it is on the fly, it is in real time. That is why we call that an online algorithm. So it is not offline versus offline. So offline algorithm means that you make the decisions for all the auctions at one time at hindsight. So we're not doing that because, in this case, definitely the online algorithms is what we prefer, which is more realistic. But the offline algorithms here can be a comparator, right? Or which we can always compare our online algorithm toward the performance of the offline algorithms. But what we desire here is essentially an online algorithm. So we have multiple challenges. This is basically a mathematical re-expression or recap of our previous challenges in one of our previous slides. So we have a switching cost. The switching cost is represented by this term. So this yn is whether we want to deploy model n or not, right? So if you deploy, if at time t plus t minus 1 at time t, you deploy the same model, there's no switching cost, right? Because these two is going to be the same, so the switching cost is going to be 0. But otherwise, if here you do not deploy the model at t minus 1, but you deploy the model at t, so you're going to incur the switching cost. And then we have this another challenge. So this term is very hard to address because, for example, at time t minus 1, right? Suppose now it is t minus 1. So then t is a future time slot, is the next time slot, right? Is the next time slot that hasn't occurred yet, right? So given that this ynt is unknown because it only will be determined or revealed as the next time slot. Now, given ynt is unknown, then how can we determine t minus 1 as a current time slot, right? In order to minimize this, note that this value is unknown. So that's why it is a challenge. A second challenge can be the minimization under the long-term constraint. This is the long-term constraint, but we want to minimize. We want to minimize so basically this part, right? So this CMT is a bidding price. It's a bidding price. So we want to minimize this term. But we are subject to a long-term constraint, right? I mean, if you choose xn to be as minimum as possible, you can successfully minimize your optimization objective, but you may fail to satisfy this constraint, right? Because this constraint requires a lower bound, which is a phi n for the sustained participation. So such challenge can be the NP hardness. We have very easily show that the problem contains existing NP hard problem, which is a minimum cost and upside problem at the special case. So that's why our problem is also an NP hard problem. And then it's economic guarantees. We need to carefully design the payment of this auction in order to satisfy the truthfulness and individual rationality. So these two are going to be defined in our slides later. So what is our algorithm? We have been able to design a holistic, solution strategy like this. We have those multiple decisions. These are our control decisions that we need to make. We need to generate values for all of these variables. So how can we do that? So we have our mechanism is basically like this. We adopt the idea of decomposition, right? As you can see in our overall mechanism here. So for each single option, or in other words, for each single time slot. So firstly, we invoke our algorithm 4, our algorithm 4, which in turn invokes algorithms 1 and 2 in order to address model hosting and bit selection. And then we invoke our algorithm 3 to address payment allocation, and invoke our algorithm 5 to do the ensemble learning, basically to determine the weights of each model. So as you can see here, so firstly, we focus on Y and Z here. So Y and Z are the whether we want to deploy the model from the model provider N, and also whether we want to deploy model of the own, right? So this Y and Z are going to be determined first, and then this Y and Z will be used as inputs to another problem here. So our original problem is P0, right? In order to solve P0, we need to extract from P0 some sub problems like P3T here, like P1, P2, which are all going to be defined later. But these 3 problems are sub problems that we're able to extract from P0. And then we, if you look at here, so we focus on solving P1 and P2, and then we use our first algorithm to get the fractional solution of X tilde here. So X tilde represents a fractional solution, a fraction decision about the winning beta selection. But you can't select a partial beta, right? The beta is either you select the beta or not select beta. You cannot select a 0.2 beta or 0.8 beta. That makes no sense. So that's why we use algorithm 2 to convert the fractional solution into an integer solution, which is also a binary solution, whether you select the beta or not. So based on these two, and then we calculate, this is beta selection. So having those beta selection outcome, we use this decision of payment. We use algorithm 3 to calculate the payment while satisfying the 2 economic properties, as I mentioned in the previous slide. And then in the meantime, having these model hosting decisions, these 2 are model hosting decisions, we can determine the weights for each single model because we want to do the ensemble learning, right? So eventually, if we combine all the control decisions, we're going to be able to provide or to produce all these control decisions. So in the next few slides, I'm going to be very quickly, going through our 5 algorithms here. So this is the first algorithm. We focus on solving X here. X is a winning bid selection. So we extract this problem as a sub problem from our original problem P0, right? So basically, that basically means we try to solve this problem and use the solution of this problem as the solution to our original problem P0. And then, so firstly, we have P1. These are directly extracted from our original problem P0. So in order to solve P1, so we relax it to P2. We also convert the notations a little bit because this is kind of like a vector format notation, making it easier for us to do the further derivations. So this is basically relaxation. By relaxation, I mean here you have integers, but here you are considering a continuous domain. This is relaxation. So later we need to run the solution, the fractional solution, back to the integer domain, right? In order to determine which beta that I want to buy, which beta we do not want to buy. Okay, so now we have P2. This is just relaxation and notation. I use the concise notation here, adoption of concise notation here, and then we need to reform the P2. This is basically a Lagrange relaxation. This is a kind of standard operation, standard mathematical reformation here. So what we can do is that we can recognize and find an existing algorithm which is called modified online set point here, whose videos I'm gonna skip, right? So by alternatively solving this and this, solving these two. Firstly, you solve this Lagrange dual variable, which is lambda here, and then you solve the primal variable, this is x here. So by ultimately solving this, we're going to be able to construct our first algorithm. So basically, as you can see, so this is equation 1 here, equation 1 here. So this is equation 2. So equation 2 is that we need to solving the problem. So because this is a convex problem that is defined on a continuous domain, so it can be solved by any standard optimization solver, right? So that's why the last one here, we're just using a whatever optimization solver. So if we do something like this, as you can see, we're going to come up with the fractional decision of X, which is a winning bid selection. So our second algorithm is to convert the fractions here into integers, right? I mean, you have many ways to do that. But what we want to do is that we need to ensure that all the fractions are rounded, right? It needs to be rounded either to 0 or it needs to be rounded either to 1, meaning not buying a bit or buying a bit. And then we need to ensure that there's no violation of continuous constraints. By that, I mean this constraint, right? These two constraints, sorry, the first two constraints. Because previously this xn is a fraction, right? We have relaxed this into the fraction. So now you are rounding this into integers. So how can you guarantee that the integers can still satisfy this constraints, right? We need to guarantee that. So in order to do that, we need to very carefully design our rounding process. So as I just said, for all the fractions need to be rounded, there is no exception. Secondly, there's no violation of that instantaneous constant. And thirdly, which is also might be the most important thing, is that we need to ensure that the expectation of this rounded integer equals the fraction before the rounding process. So why are we having this? This is basically a requirement in order to satisfy the truthfulness and individual rationality, which are also what we call the economic topics for every single option. Right? This is something that we need to deliberately satisfy, because we're going to use this. We're going to leverage this later in our payment calculation. So our payment calculation is like algorithm 3. So as you can see here, we have introduced like a very special format in order to calculate payment. So where do we get this? This is not developed by our own, right? This is set by economic literature. Is basically, personally, I can consider that as an extension of the Mearson theorem. So Mearson theorem is a theorem which is very material, is very widely used in the literature of auctions of economic mechanisms. So we cite that literature. So that literature basically says, in order to guarantee the truthfulness and the individual rationality, for a randomized auction, now our auction has automatically become a randomized auction, because in this process we are doing randomization, as you can see, with probability. We are doing randomization rounding, right? Randomization rounding. So because of that, our auction here has been kind of, massaged, has been kind of adapted into a randomized auction. So in order for a randomized auction to achieve those economic properties, so that literature of the Mearson extension literature, it says that you cannot design this payment as an arbitrary form, right? There is a fixed form. They have proved that this is a necessary and sufficient condition that we need to use. So the key here is to find the value, the value kappa here. So in order to guarantee this two, right, this two is the sufficient and the necessary condition that we need to satisfy. So fortunately, based on our previous sub problems, the problem sub problem 2, which is basically here, by leveraging analyzing that, we're going to be able to find out this value of a kappa in here. So having that value, we're going to be able to show that our own kappa, which is going to be a very concrete and specific value. That value is going to satisfy these two conditions. So this is basically the payment application. And then we have the model hosting algorithm. The model hosting algorithm here, again, we define or extract another sub problem from our original problem. So we solve this sub problem here. So as you can see, this sub problem is also an integer program, right? Which basically, more than often it's going to be NP hard, right? It's going to be NP hard. But as we observe that this is actually a problem that looks like NP hard, but it's not essentially NP hard. Why? Because the constraints here actually satisfy something that is called the total unimodularity. So what does that mean? That basically means if your constraints satisfy a special format, then even though this is an integer program, just automatically relax this problem into the continuous domain, and then you solve that continuous domain, you're going to get a fractional solution, and your fractional solution is going to be automatically the integer solution. So there is no way for you to get any other fractional solution. That is basically what is said by total unimodularity. So here we focus on addressing the switching cost. So we basically we are wondering, whether we should apply our new decision here for time t, or we just continue to apply our previous time decision at t plus t minus 1, right? because if you apply a new decision, you may be able to incur switching costs. And if you continue to apply the previous decision, you are avoiding the other decision at the t will be exactly the same as the decision at t minus one. So there is no switching cost, but that is the benefit for applying the previous decision. The disadvantage of applying the previous decision is that the previous decision, how can you guarantee that your previous decision is still a good decision for a current auction, right? For current auction, the inputs have been changed. So most likely, this is going to be a new decision. It's going to be a good decision, except switching costs. So that's why we have a trade-off. So this algorithm is supposed to address that trade-off. Then the last algorithm that we would like to talk about is basically how to determine the weights, right? The alpha, basically the alpha and beta value in order to conduct the ensemble learning. So here we are using the idea of hedge weights. That is basically a standard machine learning algorithm from ensemble learning literatures. So that is all of our algorithms. So those algorithms, we put them all together and make them work together. And then we have conducted some performance analysis for our algorithms. So for example, firstly, we can analyze and prove the regret and fit, right? So regret definition is here, the fit definition is here. So what we can prove is, actually we can prove theorem one, right? We can show that the regret and the fit has an upper bound. And more importantly, this upper bound is sublinear upper bound, right? As you can see, the exponent here is less than 1. That basically means this upper bound even grows slowly than time, right? So as if time goes to infinity, this upper bound is going to be 0, right? That is basically what it means by sublinear, right? So sublinear basically means that, if time horizon long enough, so ideally, right, this is going to be, the bound is going to be 0, right? Which basically means there is no difference between these two. There is no violation between our sustained participation constraint. There's no violation for that constraint. So, and then we can define the utility based on which we can further define truthfulness and individual rationality. So what does that mean? That basically means that, so firstly, what does utility mean? Utility basically, as you can see here, so this is for a bidder or for a bid, right? The PM is the payment that is received by the state, right? It's paid by the auctioneer, it is received by the bidder. It is some money that you receive, right? So the money that you receive, subtracting the cost, right? It's something like a revenue concept of like revenue. So this is utility. So the truthfulness basically says that in order to maximize this, you want to maximize this, right? Because this is the payment, the revenue, the money that you receive, the cost that you pay, the difference. If you want to maximize that difference, well, the best way to maximize that is to not lying about the bidding price. I mean, you can lie about the bidding price, right? If your cost is $10, for example, you can say that, oh, my cost is $15, right? Because I expect you to pay me $15 because I want to earn more money. Right? But this truthfulness basically says that is going to be doing harm. So you're not going to have any benefit, So the best way for you is to tell the truth, of your bid. So why is that? Because here you want to maximize the utility, and the truthfulness basically says this. So this is the definition, right? Another definition is that there's the utility is always negative, so always non-positive. That basically means you do not lose money. You either earn 0 money or you earn some positive money, but you do not lose money. So these are the definitions. These definitions are not automatically satisfied. It needs to be. It can only be satisfied as long as we design our payment very carefully. Like how can we calculate our payment so that these three can be satisfied? I mean, they are good properties, right? They are good properties for every single auction to satisfy basically some standard properties. So they are not automatically satisfied. The only way to make them satisfied is to very carefully design our payment approach. So we are able to prove another theorem. So this theorem, as you can see, there are 3 conditions. These 3 conditions are not from outside; they are from our existing classic literature. So what we can do is that now we have these 3 conditions, right? What we can do is that we can prove our own auction mechanism can indeed satisfy these 3. Because if you satisfy these 3, you're going to be able to guarantee individual rationality and truthfulness. So how can we show that? As we just mentioned, so we need to we need to concretize the PNT, right? It just report our previous payment maybe very quickly. So this PNT is designed like this. So this, as you can see, this is x n tilde. X n tilde is determined by our algorithm 1, right? So and also this x n bar is determined by our algorithm 2, right? So our algorithms, they are all working together in order to satisfy these 3 conditions. Because of that, we can satisfy these 3 conditions, and then we claim the truthfulness and individual rationality can be satisfied. So actually, we have another 2 2 theorems which I'm going to be skip actually. So the theorem 3 basically means that for the inference loss is here. As you can see, this is one component from our objective function. So we can find an upper bound for this inference loss. So and then theorem 4 basically says a competitive ratio. We can also find a competitive ratio here and just observe this inequality. So what does this inequality mean? Which C is the value of our objective function incurred by our own online control decisions, meaning the control decisions produced by our proposed online algorithms. So this C star, is the offline performance, right? As you just recall at the beginning of this talk. So we mentioned that we can always do this offline performance as a comparator, right? So our goal is to, of course, is to minimize this ratio. The ratio here is a max between R1 and R2. So what is R1? R1 is defined here. What is R2? R2 is also defined here. So we derive this R1 and R2 from our algorithms, right? So basically, we can prove that this inequality can hold, so that the multiplicative gap between our own solutions and the best solutions, offline best solutions, is is this as large as that times, right? So that is basically some of our theoretical analysis. So after that, we are interested in doing some experimental evaluation. So we are adopting 4 real world data. So if you can refer to our paper, you are going to find all the details for these inputs. So and then we have some models, different type of models, and then some for training, some for testing. Testing means that they are used to produce data streams, right? And then we have the cost bin. So for every parameter, we will find an appropriate value for every parameter here. So we use real-world cloud locations and use geographic distance as an approximation of the downloading cost, and use the real-world electricity price to simulate the hosting cost, the simulated energy consumption. And also we have this bidding price. I think that this value also comes from existing literature. And also we have this auction budget. We can specify a range of this auction budget, and also the ensemble requirements, so that we can do we can always vary these numbers in order to generate a range of different evaluation results. And the sustained participation threshold is uniformly generated from the range of 0.1, and the model variation we assume is not changed by default. So number of time slots, or in other words, the number of continuous auctions is set to be 100, and then we consider multiple approaches for comparison. So we have the random approach, have the greedy approach, and also we have 2 approaches that is basically adapted from state-of-the-art ensemble learning algorithm. Without the state-of-the-art ensemble learning algorithm, they focus on producing the weights. They do not focus on how to get the base, right? So we actually use our greedy approach here, to determine the winning bid selection and model hosting, but only use this 2 state-of-the-art ensemble learning approach for the weight determination. And eventually we have the offline solution as our benchmark, right? That is the best solution that we cannot beat, right? Because offline, I mean, you determine everything at hindsight, but all these algorithms, including our own algorithm, they are online approach. So the online approach compared to offline approach. Our hope is that we would like to be as close as possible to the offline approach. That is what we want. So we have produced many evaluation results, and more evaluation results can definitely be found in our paper. But here I just show a subset of our evaluation results. So we evaluate social cost, and we show that our approach has the best social cost. This is basically like a real-time social cost. The social cost means the total cost of the entire system. So, and also we show the truthfulness. Only being the true price can you have the maximum utility, and showing the individual rationality basically means the bar is always no lower than the curve right? Because your individual rationality is non-negative. And then we show the regret, which is supposed to be sublinear, and the fit is supposed to be sublinear. And also the real-time accuracy, we compare all those different approaches to show that our approach can we cannot beat offline, right? But we are second just after offline, better than all the other alternative approaches. And then the cumulative accuracy and also the execution time. I mean, if you we have implemented all our algorithms in Python and in the standard like desktop environment, so we can very easy for us to measure all those all the running time. So this running time is really in the I think it's in like in seconds, right? But we are considering like 100 auctions. I mean, how does each auction last, right? I mean, if each auction lasts like if each auction lasts like in a minute, for example. I mean, for example, this algorithm is going to return the results in about like 1 second, right? So if compare 1 second to 1 minute, so definitely it's kind of like a very mild and moderate execution time performance. So basically, that's the end of our first piece of work. And even in this slide and the next slide, I'm going to very quickly talk about some other research about this auction assisted AI systems. So here we can so in this work we are working on the edge AI inverse. So in the previous work we talked about the cloud AI, right? So there's one cloud, there's one service, and the setting is very simple there. But here the setting is the problem scenario is like this. So you have these edge devices. The edge devices can be a edge server, can be a mobile device, can be your smart router or whatsoever. So these edge devices, you know, they belong to their owners, right? So now we want to incentivize those owners to contribute their resources, their free resources, to run the edge computing task. So that's why we can set up an auction here, right? So this auction, this is an edge inference service. It can make payment to these bidders. So these bidders can bid their resources instead of models. So in contrast, in our previous work, in the work that I just talked about, we are talking about auctioning the models. Here we are auctioning the resources. So it's different. So in another piece of work, we are considering the problem of foundation model fine-tuning, right? We have a lot of foundation models, and then fine-tuning basically means that you get a specific data set and use this data set to kind of like retrain that model in order to improve the performance of the foundation model on your specific data sets or on your specific task. So there is an approach called the LoRa approach or multi-LoRa approach. It's basically you do not need to retrain your entire model. Instead, you just retrain an adapter, right? An adapter. So you insert or inject the adapter into your existing model without changing your model, but you just change this adapter, right? And then by making these two working together, you are going to be having a customized model, having a fine-tuned model. So this is a very special task. It's called foundation model fine-tuning. So now here, if you just consider that there are a lot of different fine-tuning tasks, right? And each task is willing to pay some money for execution in the cloud environment. So as a cloud service provider, so how can you charge or how can you bid, how can you price these fine-tuning tasks based on the special characteristics of each fine-tuning task? That is basically another scenario that we can apply the idea of auction. So for the future directions, we have some of the directions that we talk about are as follows. So for example, the first direction is auction that adjusts selection rules based on real-time AI model feedback, right? So we ensure truthfulness and individual rationality when the AI model performance is unknown, right? And integrate auctions with maybe with another algorithm which is called multi-interdependence. That basically allows us to make the winning bid selection decisions without knowing the AI model performance. But as time goes, you're gonna test which model is bad. And then you try to always choose those good models and avoiding choosing those bad models, something like that. And then we can design some contract theoretic mechanisms for the AI system, which is select the winning base. I mean, there are some special concerns and questions that we can ask here. And the last can be the real-world implementation and deployment for our auction mechanisms in the real-world cloud edge environment. So in this work, in all these efforts as I've just talked about, so we do not have got a chance. We didn't have a chance to do the real-world implementation, just to run our lab environments by simulations. But if there's a chance to do the real-world implementation, definitely we're going to be getting more like measurement results, implementation results, and hopefully some more interesting results. So, sorry. Finally, some acknowledgements. So we acknowledge our faculty collaborators and also the students, PhD students that directly work with me very closely on those papers, and also acknowledging the NSF grants, and also the support from the Center for Cybersecurity and Privacy at University of Oregon in the US. The last slide, this is really the last slide, is basically the recent 10 publications on the auction-assisted systems from lab. It's just for reference. If you're interested in talking about any of them, just let me know. Thank you.